Ash clouds and pyroclastic avalanches engulfed Indonesia's Mount Semeru, Java's highest peak, as the volcano unleashed a series of explosive eruptions through mid-November 2025. On November 19th, Semeru erupted 10 times in a single day, roaring to life after a relative lull. What triggers such a burst of activity in an otherwise intermittent stratovolcano? Could shifting plates deep below Java have set a cauldron of magma boiling over? And what hidden dynamics within Semerus summit cone determine whether its next blast will be a routine ash puff or a catastrophic pyroclastic surge? These are the questions confronting volcanologists as they investigate the latest Semeru crisis. The sharp exodus of villagers and climbers was no surprise, for this stratovolcano has long harboured the potential for deadly pyroclastic flows and towering ash columns. Yet the sheer scale of Semerus November eruptions has renewed concern about processes that drive Java's fiery ring of fire. Far from mere scenery, the towering shape of Mount Semeru conceals a restless magma system. The recent blasts, the 10th set of eruptions in 2025, demand a close look at the geologic engine beneath Semerus summit. Mount Semeru's November 19th to 20th eruptions produced truly immense ash and gas plumes and blazing flows of hot volcanic material down its slopes. Indonesia's volcanology agency reported that ash columns reached altitudes of roughly 2,000 meters, or about 1 mile above the summit, while pyroclastic currents, which are searing avalanches of gas, ash and rock, surged up to 13 kilometers, or about 8 miles from the crater. Satellite data confirmed plumes shooting far higher, to an altitude of about 16 to 18 kilometers, or roughly 54,000 to 59,000 feet on the afternoon of November 19th. Such towering ash clouds briefly sprayed ash over villages downwind, turning skies dusk grey and forcing evacuations. On the flanks, video and satellite imagery captured incandescent pyroclastic flows racing down Semerus' southern valleys. Indonesian officials noted one glowing avalanche hurtling along the steep Besuk Kobokan drainage, which is the same channel that funneled deadly flows in past eruptions. According to the GVO, these pyroclastic currents roared through deep ravines, carrying red-hot rock and gas up to 13 kilometers, or about 8 miles, toward the southeast and south, before finally slowing. The extraordinary length of these flows, which is well beyond the usual 1 or 2 kilometre excursions seen during milder eruptions, underscores the high energy release of the recent events. An eyewitness photojournalist's camera recorded the collapse of hot lava into fast-moving currents that swept through forested valleys, scouring the landscape of vegetation and leaving a thick coating of grey ash in their wake. A pyroclastic density current from Mount Semeru raced down the volcano's flank during the November 19th, 2025 eruption. Such currents, dense mixtures of pumice, ash and superheated gas, flow down valleys at hurricane speeds and can travel many kilometers or several miles from the vent. Witnesses described the flow as a cloud of incandescent gas and ash surging ahead of the eruption column. In fact, the flow contained the classic two-part structure of pyroclastic density currents described by volcanologists. There was a fast ground, hugging basal flow loaded with chunky debris, topped by a turbulent ash-rich cloud that lofts buoyantly off the surface. Within that grey-black cloud, temperatures often reach several hundred degrees Celsius or several hundred degrees Fahrenheit, which is hot enough to make ash very sticky and to ignite any flammable matter in the flow path. Crucially, a pyroclastic density current derives its momentum from gravity. Once initiated, it does not require continued eruption at the vent to race downhill. In Semeru's case, steep drainage channels acted as natural conduits. The collapsing mass of hot debris coursed down these valleys, sometimes picking up distance as it entrained air and mixed with overbank ash. In previous months and years, Semeru's pyroclastic flows were usually modest, often only a few hundred meters or a fraction of a mile to a couple of kilometers or around 1 mile long during routine lava dome collapses. In late June 2023, for example, a single pyroclastic density current travelled about 5 kilometers or roughly 3 miles to the southeast. In stark contrast, the November flows traversed more than double that distance. Along with scorching, ground-hugging flows, the eruptions belched high ash columns that sprayed fine tephra over broad areas. Villages on the mountain's northern and eastern slopes found roofs and fields buried under layers of volcanic ash up to 1 meter or about 3 feet deep. The ash itself is composed of tiny rock shards, and glass formed as the erupting magma fragmented. As shown in the image above, this blanket of white-grey ash still coats homes and even a shrine the morning after the eruption. Such fallout deposits can collapse roofs and contaminate water supplies, adding to a volcano's danger zone well beyond the area of flow travel. While the glowing pyroclastic density currents swept only certain valleys, the ash plumes circled high into the atmosphere and drifted downwind for many kilometers or several miles. Air quality sensors later recorded hazardous concentrations of volcanic aerosols and sulfur dioxide in towns tens of kilometers or many miles from Semeru. The combination of fast flows and widespread ash is a hallmark of violent silica-rich eruptions. Semerus magma contains enough dissolved gas to drive explosive fragmentation, lofting ash high, but also enough viscous lava to form an unsteady dome prone to collapse. A village shrine is covered in fresh volcanic ash after Semerus November eruption. Pyroclastic density currents, like those from the eruption, can leave deep deposits of hot ash and rock in their path. The United States Geological Survey notes that pyroclastic flows typically spread ash that can blanket terrain from under 1 meter or under about 3 feet to scores of meters or many dozens of feet thick, depending on the flow volume. In Semerus 2021 disaster, villages ended up buried under several meters or many feet of hot debris. Even in 2025, local reports mentioned thicknesses of the order of centimeters or fractions of an inch to over 1 meter or over 3 feet on houses near the ridge. Beneath these new ash layers lie lava boulders up to 1 meter or roughly 3 feet in size, which is evidence of the blocky clasts carried in the basal flow. The geology of Semeru's flank, with its steep canyons and river gorges, channels these flows. Here, pyroclastic currents act much like hypercharged debris avalanches, following topography to extend their reach. They knock down or bury nearly everything in their path and leave a scar of raw, barren rock behind. How did Semeru produce such a ferocious outburst? The answer lies in the volcano's magma plumbing, which is a combination of fresh supply from depth and transient domes perched at the crater. Semeru sits atop the massive subduction zone where the Indo-Australian plate dives under the Sunda arc. This long-term tectonic setting melts the crust and mantle, generating intermediate to mafic magmas that rise toward the surface. Geochemical analysis of Semerus ejecta shows a basaltic andesite composition of around 55 to 57% silica by weight, typical of arc volcanoes. But even within this composition, scientists have identified two slightly different magma types beneath Semeru. One is a volatile, rich basaltic andesite, the other a slightly less evolved olivine-bearing basalt. Each type occupies its own reservoir chamber or layer under the mountain. The less viscous and more gas-rich magma, which contains plentiful water and sulfur, ascends relatively quickly to the surface, fueling explosive bursts. The more crystal-laden magma, in contrast, must build greater pressure to force upward. In the lead-up to eruptions, the gas-rich magma can infiltrate and pressurize the dome. Indeed, petrologists studying Semeru's deadly 2021 eruption found clear signs of this process. Increased sulfur dioxide emissions and harmonic tremors detected weeks before that eruption pointed to magma ascent from depth. These observations coincide with the idea that rising magma was priming the system and destabilizing the summit's lava dome. Eventually, the pressurized dome or vent wall began to fail. As molten material was thrust upward, the dome's steep flanks collapsed under gravity. United States Geological Survey models indicate that such lava dome or flow collapses are a primary mechanism for generating pyroclastic flows. Without a towering plume to carry it skyward, the incandescent magma simply spilled the vent like a boiling pot that tips and it boils over with the blazing front surging downward. In this way, even an eruption that seems merely effusive can immediately turn deadly. Semerus crater, known as Yongring Siloko, has indeed been observed steadily growing an extrusion over the past few years. Satellite heat data confirmed recurring hot avalanches on the flanks throughout 2023, and field reports describe small flows reaching up to 2 kilometers or about 1 mile from the summit during spring of that year. After this first mention, remaining distances in this section will be metric only. Such flows often reached 1 kilometer to 2 kilometers during routine events. The November eruptions appear to have followed this pattern on steroids. After a period of white steam emissions, Semeru's vent likely accumulated enough hot lava and gas that it suddenly gave way. The instantaneous decompression sent rock fragments and gas skyward, seen as the 16-kilometer to 18-kilometer ash plumes, and triggered massive avalanches of the hot dome front. Convection currents may have driven part of the material upward, but much of the mass collapsed straight down slope. Witness accounts of the eruption describe a near-total darkness at 4 o'clock in the afternoon as ash dust blotted out the sun, which is exactly the scenario of a collapsing column. In one compelling shot, a dense grey cloud can be seen pushing horizontally through a valley. A classic sign of a collapsing column feeding a ground, hugging pyroclastic flow. A question remains whether heavy rain could have played any role as it did in December 2021. In that event, intense rainfall was later found to cool the flows to the point that even surrounding trees and plastics were not charred. For the November 2025 eruptions, it is not yet clear if precipitation was a factor in modulating flow temperature. Reports do not emphasize unusually wet conditions this time, and climbers were caught by surprise rather than warned of lahar risk. But the physics of dome collapse and column failure alone are sufficient to explain the violent scene. The underlying tectonic setting also framed how this eruption unfolded. As Reuters noted, Indonesia straddles the Pacific Ring of Fire, where the Eurasian and Indo-Australian plates interact. This plate interface is rife with seismic fractures and magmatic underbellies. Java Island, lying above the Sunda subduction trench, is studded with one of the world's highest densities of active volcanoes. nearly 130 in total. Semeru itself rises about 3,676 metres, or about 12,060 feet above sea level, which is the loftiest point on Java. After this first mention, remaining elevations in this section will be metric only. Its summit crater drains southward toward the Indian Ocean via steep gullies like the Besuk-Kobokan, which is a long-known channel for lava and debris flows. Past eruptions have repeatedly showcased this duality, small to moderate explosions punctuating decades of quiescence, interspersed with occasional larger pyroclastic flow generating blasts that reach the lower flanks. Historical records confirm that 19th century and 20th century eruptions were typically modest, but sometimes produced large flows. In recent times, Semeru has been quite active, with a continuous eruptive phase underway since mid-2017, dominated by steam and ash emissions and repeated glowing avalanches. Even the major collapse of December 4, 2021 stemmed from these chronic dome-building processes. That calamity killed dozens and buried entire villages, reminding scientists and residents that Semeru's persistent activity can easily leap into catastrophe. In mid-2025, Semeru's behaviour had already been unusual. Indonesia's Magma Centre logged 2,803 distinct eruptive events at Semeru through November, which was vastly more than any other volcano in the archipelago for the year. In just the 7 days, up to November 19th, the volcano produced 9 separate emissions. These were mainly weak emissions, with ash puffs sometimes reaching a few hundred metres above the crater. But the pattern signalled swelling unrest. Most eruptions barely disturbed the alert status until the climactic November sequence. When the blasts finally came, officials raised the warning to level 4, which is the highest, and set exclusion zones, accordingly keeping people at least 8 kilometres or about 5 miles away from the crater and far from river channels where pyroclastic flows or lahars could follow. Semeru's recent surge of activity is not unique in character among stratovolcanoes worldwide. Geologically, it resembles cases such as Java's own Mount Merapi or the Soufriere Hills Dome eruption in Montserrat. Volcanoes that quietly extrude viscous lava until a dome collapses. For example, Merapi's 2010 eruptions produced fast pyroclastic flows, sweeping several kilometres based on a similar mechanism of lava dome growth and pressure build-up. A Forbes analysis of Indonesian volcanoes pointed out that Merapi killed 350 people that year, largely through such flows. The Semeru event shares this lineage, silently simmering, then sudden structural failure. Even on other continents, comparable episodes occur. The United States Geological Survey and National Geographic describe how collapsing magma columns or domes can unleash flows that travel tens of kilometers, incinerating forests and cities in their path. Pyroclastic flows of this kind are among nature's most destructive agents. Back at Semeru, the question now is what comes next. The recent eruptive pulses have likely unclogged part of the system, but they have also potentially opened new vents or fractures. Experts note that erratic cycles of dome growth and collapse can continue as long as magma supply persists. Seismometers have already been registering fresh avalanche quake signals of rock collapse inside the crater as late as November 21st, even after the major eruptive phase. The volcano's gas output remains high and ash plumes still billow between blasts. In the short term, surveillance is focused on the same hazards: renewed pyroclastic surges, lahars when rains come, and heavy ashfall. Geologists will comb satellite images and crater observations looking for new dome formations or magma intrusions. If the November sequence was triggered by a fresh batch of deep magma, more activity could follow. One thing is certain. Mount Semeru exemplifies how life above subduction zones can be precarious. Its height and grandeur belie a perilous interior, one that pulses with the Earth's tectonic heartbeat. Each eruption is a window into that fiery engine. By piecing together the signals, seismic tremors, gas emissions, and the chemistry of ash clasts, scientists build an increasingly detailed portrait of the magma plumbing. Publications have already mapped out 2 distinct magma reservoirs and documented pre-eruption tremors at Semeru. Now, comparing those scientific models against the raw drama of November's eruption will refine our understanding. For local communities and officials, the practical goal is clear. Use this knowledge to anticipate the next blast, as forecasters do elsewhere, by monitoring volcanoes like St. Helens, Popocatépetl and Hawaii's Kilauea. Each eruption at Semeru, from the routine ashes to the extraordinary flows of this month, writes another page in the volcano's story. And geologists studying that story know the stakes. Semeru can erupt again at any moment, powered by the very forces that continue to build and reshape our planet's crust. If you found this breakdown intense and eye-opening, make sure to hit that like button, share this with anyone who needs to stay informed, and subscribe so you never miss the next deep dive. And don't forget to tap that hype icon. It helps push this video out to a wider audience and keeps the momentum going.